Okay, today's video, one second. So this dog is called Rocky. I have two. This dog is called Rocky. You go Rocky, you go Riley. Now Rocky is no Labradoodle, the Beagle. Now the Beagle has a patch in the eye. So my one of my wouldn't say it, but I just remember this. So the Beagle has a patch in the eye. The Labradoodle doesn't. So this is the difference between the Beagle from the Labradoodle. The Beagle has a patch in the eye. Which is a black patch or white patch. It doesn't matter what the patch is. But the patch in the eye is like an eye patch. Now, this dog is called Rocky. Now, R for Romeo, O for Oscar, C for Charlie, K for Kilo, Y for Yankee. Now, Rocky is a beagle, and the beagles are a Labradoodle breed. So you get heterogeneous, homogeneous. So I'm trying to create a classifier for dog, what I call dog classifier. So my algorithm should use a dog classifier to write a classification. So be a verb noun modeler. So verb now the verb this is the verb is category, but the verb is verb. You get a noun, so the dog type. So the verb would be a verb noun classifier. So the verb is a heterogeneous, homogeneous classifier for system for dogs. So you go a Labrador, you go a beagle. Now the system between because this is a classifier. This iPad is just one feature of a beagle, not like Labrador. You're gonna have two stuff, but this is a beagle dog. So this dog is called Rocky. Now Rocky is one of my dogs, and you have Riley, Rocky and Riley, which is a canine dog. So I'm gonna own a canine dog and a Labrador and a beagle dog when I live here, when I get a house. They got the two dogs that I have. I'm gonna call them the same names, but this is how they look by default. Now, basically, because they look just like this by default, this is how they look. They look. They have attachment to people that are moving on adapt. So it's gonna be a constant matching of the system of non-latency. For example, my goal is to literally have my AI classify and recognize the dogs. My AI is called ontological Bayesian intelligence architect, ontological AI. So the AI knows what they do, and they work on one principle, one principle, four main principles. P now P such that S implies D. Implies an arrow, so implies D. P given a state implies some data in that state. Think of it like let's call it this is OpenAI AI systems. They're called a probe. P is a probe such that X is a state implies D some data that was there. So P is external. P external P. P stop external. EP. Now, EP has an IP as a function. Now, IP stands for I as a function of P is a data, some data, such that the data, there's some data input, you have to input and apply some state. So it's like, it's like a telemetry system basically. But it's a probe system. So the beauty of this system, the state is a Lexa, a parser, or a semantic graph called an EST. A semantic graph. Now, the semantic graph is canonical. I can't remember how important it is, but you're gonna have a half signal. You're gonna have a half a signal measurement. Is this a dog? So is this a dog or is this a dog? Is this a cat? This is a binary classifier. This is a verb classifier. So you're gonna have is this a dog? So ask is it a dog? Is it a cat? Yeah, ask, is it a kind of is it a kind of is it a type of a cat? Is it a type of is it a kind of cat? Is it a type of cat? No, so is it a type of cat? Is it a type of dog? Is it a type of sorry, is it a type of dog? Is it a kind of dog? Now the kind of dog needs to but then the four questions that can be broken down instead of a binary classifier, dog or cat. Now, dog or cat is one example of the system of Labrador. This is a beagle here, but this is a beagle, but is it a Labrador or a beagle? Is it a Labrador? These are two types of dogs, but they can be mistaken for other things too. So, the goal is to have this system probabilistic based on Bayesian inference. Now, Bayesian inference is going to classify this thing properly. So it's gonna map onto some kind of fashion. This is Rocky. This is Rocky. Is gonna be one of my dogs because I like beagles. But this is a beautiful picture because I remember seeing this in my dreams. I remember Rocky. I remember Riley. This is Rocky the dog. From one of my things. So I call it Rocky because there's some kind of connection to the word Rocky. But I have Rocky and Riley, like Riley. So they are both what I call Rocky's the male or female. Rocky. Riley's a unisex name. Rocky is not. Yeah, The Rock. Yeah, Rocky is a unisex name too. Because it doesn't stand to gender. Even the name is chemical. So this picture is just one picture I'm going to use to classify some information based on the set code. But this rocket, so what is Riley? So Riley is the canine dog from Call of Duty Ghost. Riley dog, that's one of my dogs. So this I have digital dog. Those two dogs that exist and they're very happy to see me. I hope so. But I love them. Hi. They look very happy. This is a photo of them. So it's kind of because I remember they have this dog in the photo. So I'm gonna go with this kind of system of the belief system. So basically, the half measurement principle is so important to understand. Because if you say if a dog, you get a signal. So it is 4 reads and 2 writes. So 4 reads of an image, and before you calculate it, you do 2 writes. So you gotta have half of that. So a read is called 4 reads and 2 writes. And this is basically the default OpenSS way of a system, but it's not the half single. So this is obviously this is a lattice operation, 4 reads and 2 writes. We're gonna have a half of 4 reads and 2 writes to be one half of 4 reads will be 1 divided by 4 times 2. That will be 2/1. That will be 1 times 2, which is one half. You have one half of the measurement of this photo to classify whether it's one of the heterogeneous counts. So this will be in a tensor. This will be in what is a 4D tensor. Now the 4D tensor represents a system of 4D, whether it's basically a 4D tensor, because you're gonna have space and time dimensions to offset the dimensions of this is what is moving or not. What is just a image or not. But if it gets a 3D map of the image, you're gonna have a kind of this thing. So I'm trying to take this image and an image of Riley the dog from Call of Duty Ghost, which is a military dog from the video game I played, Call of Duty Ghost, to map onto this system of 4D, basically on structured unboxing, on structural unboxing. So I'm going to unbox the data by their features. So the features will be having an eye patch or not, or which is the distinction of a beagle from a labradoodle, and or distinction from from any cat, whatever. Because cats don't have no eye patch, but it's a variation. So the classifier again is it a type of cat? Is it a type of cat? Or is it a species of cat, or is it a type of cat, or is it a type of dog? Based on the phenotype, the physical features, and the genotype, the makeup of the genomes that determine the features. Based on, so it's kind of probably the system, but this is efficient to classify my ASN, or my ontological basis, to classify my dogs. I'm looking at my dog in real time. So I have to upload. So we go to github.com/github.com/O for Oscar, B for Bravo, I for Indigo, N for Delta, E for Echo, S for Zero, S for Zero, E for Robert, S for Zero, S for Sarah, MK2, N for Mike, K for Kilo, number 2, you / let me also include repository. Rocky and Riley. Rocky and Riley. So I call it Rocky and Riley. Rocky and Riley. Rocky and Riley. Which are 2 dogs, basically. These are 2 dogs. But they're 2 dogs of a system of a half measurement. So then I have 1/4 times 1/4. 1/4 1/4 times a half. 1/4 times 4 reads and 2 writes, which would be 1/2 read and 1/4 which is 1/2, which is 1 times which is 1/4. So you can have a quarter write, no, a quarter read and 1/2 1/4 write, and no, a quarter write, no, a 1/2 write operation and 1/4 read. I'm then gonna have the 1/4 times 1/2. These are called quantum measurements using classical measure. So basically, the signal I'm gonna the second contain a signal of a 1/4 matrix. So we got times the whole matrix, whatever the system. But this is a placeholder for computation. So you can detect, you can give it time to classify. Basically, the system has to determine what this feature is based on the square. So this square is one classifier of a dog and a cat, but it's a very big, very good to understand that you cannot fake the system, cannot lie system. So you cannot lie system, but you gotta have 1/2 measurement, 1/4 measurement, which is 1 divided by 4, and you get 1/6 and 1/8 based on conjugate pairs of binary systems, which is 1/2, 1/4, 1/6, 1/8. So you can have a full information spread over the tensor. But this is basically to stop the binary problem propagating as an error threshold. And so you can have a signal of what it is, or ratio of measurement between 0 and 1 for each dimension of continuous convolution. Dimensional principles of convolution. Dimensional represents to the 4D tensor, 3D tensor, 2D tensor, and 1D tensor based on the scalar properties of what's using tensor flow. So this is I'm going to try to clarify this. So thank you for watching the video. Thank you for the video. So so what's the last principle? On structural unboxing, basically structural unboxing is the concept of starting with something with structure and unboxing the properties via a 4D tensor and 4D tensor. Or you can have a 3D tensor, whichever suits the data set. We can use a 3D tensor over 2D data set. We can spread that over the 4 KN in custom. KN's nearest neighbor cluster, which is a cluster of machine learning algorithms, via the system of structure where you want the data, how the AI wants to classify the system of unknown miscellaneous data you can even classify in the data set. Thank you for watching this video, guys.